Cool. Why is this microphone so loud? All right. Is this OK? Awesome. OK, let's keep going with efficient things. We talked a bit about efficient training last time. Let's do efficient inference today. And we'll keep it relatively short. I really just want to talk about speculative decoding and some variants. We're not going to get into like the entire space of techniques, of which there are a whole ton. We should have time at the end of class. So if folks have questions about presentation or project, I'll hang out. You can ask me questions. Of course, you can do that during office hours, too. OK, so here's the logistics. Homework 2 is still in progress. It sounds like there's at least some interesting things going on with homework 2. Continue signing up for presentations. And I think this week is when we're releasing project information. But you are welcome to start forming teams and thinking about what your project is. A bunch of you folks have already asked me about that. And like, I encourage you to keep asking ahead of time. We're doing this last lecture on efficient inference. We'll do eval on Thursday. And then we'll start talking about a bunch of sort of extra topics. So agents, more stuff on reasoning, and multimodal models. So we haven't really done anything outside of language for the most part today. We'll focus much more on that coming up in 2 weeks. Cool. Any questions about the roadmap? Or anything else in the class? Sounds good. All right, so we'll very briefly review last time, where we talked about things like flash attention. And that was more about efficient training, although they also apply to inference as well. And then we're going to move on to speculative decoding and a couple of other efficient inference techniques. I'll keep this part, since it's a review, relatively short. So we talked about the reason for all this efficiency business. And it is because of the scale of models. So we saw this example of how long does it take to train if you have a huge array of GPUs. And the conclusion we came up with is basically that if you have 1,000 to 10,000 GPUs, and you're training a model that's kind of full scale, so 70 billion or 175 billion parameters, you need somewhere on the order of 1 million GPU hours. And of course, that's really why you can't train these things on just a handful of GPUs that you could access. And then we spent a bunch of time talking about this technique called flash attention. This was kind of a clever way of using the GPU better. And it said, hey, you should not ignore exactly what's happening on the GPU. Just because your framework, like PyTorch, can figure out how to use CUDA doesn't mean you can sort of blindly do that and expect things will go fast. So flash attention had this really simple trick where it said, hey, we have a little bit of very fast memory. Let's do as much stuff as possible there without going back and forth to slower memory. OK, so this is something we spent a bunch of time on last time. Everybody comfortable with it? Cool. Doesn't really require you to do anything. If your devices and if the training framework you're using is compatible with flash attention, then someone's implemented it already. And you can just turn it on, and things will go faster. So this is something that you're not really going to implement yourself, although it's pretty interesting. And the reason why this thing worked was this kind of very interesting trade-off, which said something like, normally, if you recompute stuff, you spend less in terms of memory, but you lose something in terms of time. But here it turned out that if we spend less in terms of memory, we can stick to much faster memory. So we actually don't lose anything in terms of time either. We get something that's better kind of on both fronts, which is interesting. So expect to see benefits of 2 to 3 times in terms of training speed, which is pretty substantial, especially if you're talking about training for months. OK, and then we talked a little bit about parallelization. But really, the story was, hey, we have this picture over here. We want to make sure that we have as little free time for our GPUs as possible. We want to parallelize things in such a way that nobody is waiting, at least to the extent that we can. We're getting the maximum amount of utilization as close to 100% as we get. And we talked about how there's a few different techniques that can help you achieve this. Of course, for our class, it's unlikely that we have access to 1,000 GPUs, so we don't have to worry too much about implementing these kinds of techniques. Any questions on this stuff that we talked about last time? Everyone's happy? Cool. All right, in that case, I'm going to skip questions, and let's just talk about the actual inference part, which is the interesting part. And the goal, of course, was exactly the same thing as training. But as I mentioned, it's interesting. Even though you think of training as this more heavyweight thing, the amount of time you spend training versus the amount of time you spend deploying your model and doing inference is actually lower. So really, you will see more of a gain when it comes to improving inference than improving training. And this is especially true because you can't parallelize inference quite as much as training. In training, we have access to all the tokens, including the future tokens. So we can start doing things like parallelizing over the tokens. We can't do that at inference time. And why is that? Yeah. Yeah, but what does that mean? Right. We don't know the future, right? We don't know future tokens that our model is generating. So we're stuck waiting for each token to be created at a time. And then we have to plug it back into our sequence and generate the next token and so forth. So I cannot generate 5 tokens at once, even if I have the devices to do that with. I have to wait for the first token to be done to generate the second token and so forth. That is not true for training. I know the future tokens already. They're in my training set. They're just text. Everybody see this key difference? Cool. So that's the reason why if we do get more efficient at inference time, we actually will see more of a benefit, at least in the sense that we'll see something happen much faster. Cool. All right, so some examples. You can see different techniques that get you to 3 times speed and beyond. One more question for you guys. If we recognize that this autoregressive nature is really why we're slow at inference time, what would be a solution for us? Well, I can't generate pairs, right? Because if I try to generate a pair, I don't know what the second element of the pair should be before I generate the first one. However, you're kind of right, because we'll see kind of a trick to try to do that. But what's a more general answer? Go for it.
So we try to predict, if we create an output head that tries to predict the second token, and the third token, and fourth token, and fifth token simultaneously with the first token?
This is Giorgio's idea as well.
Okay.
And the answer is actually yes. We'll talk about that in a little bit. But still, what's an even more general thing that we should do? Go for it.
Smaller LLMs.
How will that help us? I mean, we'll be faster, sure.
Yeah.
But we still have to wait for the next token to be generated, right? OK, so if autoregressive things are bad because I have to wait for tokens to be created one at a time, then maybe the solution is to not use autoregressive models, right? Those are the things that are blocking us. What is an example of a model architecture that's not autoregressive, but I could still use for language? Go for it. Yeah, we could build diffusion models for language. I mean, we're more used to them for creating images. Almost all the image generation models that you've ever used are diffusion models. But in the end, language is not so different, right? In fact, we could use diffusion models of language, and they're not autoregressive. They generate the whole sequence at once. And they improve the whole sequence at once until we get a generation that looks good. What's the downside so far, at least? Okay, the answer is it's not as good yet, right? That's usually the answer to all of these kinds of questions. If you get something that's more beneficial in some way, you have to pay for it somewhere else, or else everybody would have adopted those models, and we wouldn't bother talking about transformers at all. So we'll talk about diffusion models for language as we go down a little bit further after we talk about multimodal models that have a diffusion component. But they are quite cool. There's actually a bunch of startups that are working on just scaling up language diffusion models. And the speed is very good. We just need to work on the quality a little bit. Cool, so let's go ahead and keep going with our efficient inference approaches. The one that we'll really spend almost the entire lecture on today is called speculative decoding. And really what it's saying is, look, maybe I don't need to wait for my current model to generate the next set of tokens. Maybe I can use some other model to guess what the next set of tokens should be. And I'll use my real language model to check if that's OK or not. And the intuition here is that checking is easy. That you can parallelize because you have access to all the tokens. On the other hand, generating is hard because you don't have access to all the tokens. So if we sort of offload the process of generating tokens one at a time to some other model that's faster, and just use our original language model to check, then we can actually go do inference a lot faster. All right, well, we'll see how this intuition actually plays out, but that's the basic idea. Then the other pieces that we can do involve sort of changing what we do and trying to essentially adapt to the outputs that we're currently producing. Why do we really need a very powerful, very large language model? It's because the quality is good across the board for all of our generations, but we don't always need a very powerful language models, right? So if I'm answering a very difficult math questions, I do want the most powerful model I can have. But if I'm just responding to a user saying good morning, any language model can give me an answer, right? So let's adapt to the actual query. Let's use less power when we don't need it, and more when we actually go need it. All right, everybody okay with that intuition? Now, this is the same intuition, as we'll see further in the class, for doing something called routing. We take the query, again, a set of tokens, and we just say, hey, let's decide on the fly which language model to send it to. So we don't have to always use the most powerful language model that we have hosted. We'll kind of back off to a cheaper, faster, less energy-consuming language model if the query is simple enough. So that's routing. We'll see how we can integrate routing into a single model using this adaptive idea. Cool. All right, so let's talk about speculative decoding. So we said this basic issue that we have is we have to wait for each token to be generated to go work on the next token. And each of these tokens has to run through the entire model, which is big and slow. OK, so if we're not generating, then we're not slow, right? Because we can compute all these probabilities in parallel. I know what each token is. I don't have to wait for the next token to get generated. I can run all of them at the same time. Everybody agree?
Talking about the training data set here?
No. No, each time you do inference, for example, you might give a prompt. You already have access to all the tokens in the prompt, right? You don't have to wait for them to get created. So this is all inference time. Nothing's happening for training. OK, so everybody agree with this? If I don't have to wait for the next token to get created, I can just run on all the tokens in parallel, and we're good to go. Cool. So essentially, processing, or whatever term you want to use here, there's different terms. This is pretty fast, but actual generation is pretty slow. So let's kind of find a way to trade off against the two. So let's use a more efficient model. Sometimes it's called a draft model for token generation. And this draft model will create a bunch of tokens. And then we'll treat those as if they were the original prompt. We'll put them into our original language model. And we'll try to verify that it's OK. OK, now what does it mean to verify that it's OK? Anybody have thoughts on this?
The probability distribution is high.
Right. Yeah, exactly. We want our distribution to somehow be compatible, right? And this is nothing too weird. We do this all the time in sampling, right? Suppose we want to sample from some very complicated probability distribution. Usually that's very difficult to do. So what we'll often do is create some other kind of simpler proxy for it. And then we'll go try to fix up whatever difference there is between those two distributions in such a way that, on average at least, the samples we created with this simpler, cheaper distribution are equal to the ones that we would have gotten from the original one. So we'll use the same principle here. Let's take a look at it in action. This is the problem we're trying to solve. What if our generated tokens have different probabilities? And what we'll do to handle this is we'll say, let's reject them if they seem bad. This is basic rejection sampling, exactly the same principle as we do in general. And what we can do here is something that looks like this. Let's take a very quick look at just one set of speculative decoding samples. What you're seeing in green is what's being generated by this draft model. So this is a smaller, cheaper model. This is something that we don't have to wait for as long. So imagine this thing being 5 times faster than the full model that we started with. That means that you can generate multiple tokens in the same time it would have taken to generate one token with the original model. So this is what we're doing here. We're generating a bunch of tokens. Those are the ones you see in green. Now, at some point, this sequence of tokens has sort of deviated from the original distribution. And when that happens, we'll say, hey, we should stop here. We should reject this last token that got created. And we should go ahead and run the original language model for one token generation. And that's actually what you're seeing on top over there. That thing in red that got crossed out, that originally was from the draft model. It was one of the cheap tokens. But that sequence is no longer compatible with the original distribution. So we decide to reject it and throw it out. That's why it's crossed out over there. And then we create one more token from the original distribution. That's that last N in blue. So that's the colors that you're seeing here. And then we continue, right? So you can treat the top line as if this whole process was generating one token from the original model. OK, so now for the second one, you keep going, right? The draft model generated 2 tokens that were accepted. one that was rejected, that was the comma over there. And then in blue, we generated that 5 token with the original model. Then we keep going to the third line, same basic idea. Everybody okay with this? Yeah.
What determines whether or not we reject the token again?
We're going to see that in a second.
Okay.
We want to make sure that our probability distribution isn't too far off. So we're going to compute the probabilities using the original language model of these tokens that were sampled using the cheap draft model. And then we're going to have a test that says, hey, if you're too far off, if this is too unlikely, you're not allowed to have this happen.
I guess my question is, how do we know that it's deviated from the original language model versus the draft model if we're not running the original language model on every token?
We are. We're running it, but we're not generating tokens with it. So all of these tokens generated by the draft model are being passed into the original model. And then we can check and say, OK, well, these distributions look like this. But the nice thing is we can do all those in parallel, right? Because we have all those tokens already. We don't have to wait. So we're using the original language model on every token. We're just not generating every token with it. Cool. So this is the process. As you can see, it's doing a bunch of steps. What is the speed up here? Well, each of these lines is sort of equivalent to running the original language model once and generating 1 token. So we're actually doing a bunch more, right? So every single green thing you're seeing is sort of an extra token that we got. Everybody see what I mean by that? Normally, you would just have 1 single blue token being generated at each of these lines. Instead, we have several green tokens in addition. Now, we could get unlucky, for example, right? You can see this in the second to last line down here. As you can see, the very first token that our draft model went ahead and produced, it got rejected. So we got no benefit, actually, right? At least for that line. Now, we don't care to have a benefit every single time. We just need to get a benefit on average. So if on average, for all of these lines, there's some number of greens, then we've received some benefit. Everybody agree? OK, now you might say, hey, well, why don't I generate hundreds of tokens from my draft model and see if I get lucky and keep all of those? And of course, the answer is, it doesn't really matter how many you generate. What matters is how soon you typically get rejected. If on average you get rejected after 3 tokens, then generating 100 tokens at a time with your draft model is not useful. Now, it can go the other way as well. If on average you only get rejected after a certain point, but you're generating fewer than that, then there's no point there either. You should increase it. So there's a little bit of a game to play here with kind of the difference between your draft model and your original model. And that will kind of tell you what you can expect in terms of speedups and what you can expect, essentially, in terms of how many of these samples you should get from the draft model. Go for it.
In the last second time, when you said the first token that was generated by the draft model got rejected,
Yes.
why don't we have additional tokens after it? We should, right? From
We are actually generating more of them. It just doesn't show you the ones here. It just shows you up to the rejection point, and then it says, OK, we stopped. But in practice, you actually always generate a fixed number of these guys. And you'll pick that number in advance. You'll say it's going to be 5, right? Cool. So this is the process, and this is kind of where we're hoping to get some benefit. Notice on the last line, we already hit the end generation token. There's nothing left to do there. We can stop the process. We don't even need to run the full language model anymore from that point on. OK, so here it seems like typically on average, we're getting something like, I don't know, 2 green tokens, maybe a little bit more on average. And that means a speed of approximately 3x, right? For each blue token from the original model, we're getting for free 2 green tokens, which means we're something like 3 times as fast as we would have been otherwise. Now, when I say that we're 3 times as fast, notice that we are doing more work in some sense. It's just not appearing in terms of how much time it takes. We're doing more work in the sense of we're running another language model. We're lucky that it happens to be small, but still that's some extra work to do. And we're running the original language model on a bunch of tokens. It's just that we can parallelize it. All right, everybody agree with this? Go for it.
I'm a little confused. For the draft model, how we achieve parallelism again instead? I know like we got speed up for like more tokens that we think is correct, the green tokens.
Yep.
So if we got like 3 green tokens, we're like skipping 3. We're like speed up by 3 times.
Yep.
But how is that parallel in the draft model?
In this most basic formulation, it's not, right? What's really being parallelized is the big language model. The small language model here is acting exactly as any normal language model. It's autoregressive. The only thing that makes it faster is that it's smaller. Otherwise, nothing yet is being parallelized. Now, there's ways to modify this to also parallelize that. So for example, one thing I can do is instead of having one draft model, I could run several. And I could do that at the same time, right? And I could hope, for example, that one or the other of those guys is going to end up producing for me a longer number of tokens. But what you're seeing here is just one draft model in regular autoregressive generation mode. Yeah?
It requires the draft model to have the exact vocabulary as the large model.
Well, at least it has to have a subset of it, right? You don't want to generate anything that's not in the original model. And of course, you have to get lucky if you don't have all the tokens from the original model too, right? You have to get lucky enough for all the missing tokens to never want to be generated in this.
With the current implementation of VLLM, they have put the constraint of the length to be equal of the vocabulary of
I mean, that's always convenient, right? That makes life easy.
but it can be a subset, right?
Yes. But again, you'll get rejected a lot if the missing tokens are meant to show up, if you see what I mean, right? Like if your generation is meant to have some token that your draft model can't produce, then your probabilities are going to be way off, and you'll get rejected frequently. So it's really good if you're actually matching it.
The skilled model would be good then.
Yeah. Yep.
Just so that I'm clear, so here the giraffe model is again doing it autoregressively, but
Yes.
the main advantage here is it's a much smaller model, so
Yes.
you can get more for it.
Yep, that's right.
And then as it's generating more and more autoregressively, for example, you point benchmark bond, and then you're verifying each of those generated tokens with the original model.
Correct.
And you're seeing whether it's abiding probability distribution.
Yes.
Then what is N? Because the original model is also autoregressively doing it once every iteration, you say?
It's once per these lines, right?
Once every aspect.
Exactly. It's only once we get rejected that we use the original model to generate a new token.
And it does this autoregressive generation after it has verified every token which is generated
Yes.
by the giraffe model.
But verification is fast.
Okay, but that
So don't have to worry.
And then one
Yeah.
autoregressive.
Yes. Because it has to do that, otherwise you cannot reject, right? You don't have access to the right probabilities to reject.
Context.
Exactly. Yeah. All right. Sorry, say again.
We are doing verification for
Original model.
Original model.
Verification is run by the
Yes. Because you're still trying to produce tokens according to the same distributions that you have from the original model. Otherwise, you're really just using a new model altogether for inference, right? So you have to make it match up. So therefore, we do have to compute those.
After each step if they are verified, then after each step if they are verifying, then after each token if they are verifying with through LLM.
No, it's much faster, right? Because I'm just checking probabilities. The token's been generated. I don't have to go through the process and put it back in. I have access to all of them. So if my draft model creates 3 tokens, I have access to all 3 tokens. And I can run the original model on all 3 of those simultaneously. Yeah.
Curious, we were discussing, so what portion of the model do you pass the input sequence through that makes it so much faster than just the entire decoder? Is it like part of the decoder or?
No, it's a full forward pass all the way up till the end.
Okay.
I just parallelize it. That's the only difference, right?
Oh, okay.
If I generate 3 green or 4 green tokens, right, I can just do it all at once.
You know all of the future sequences.
Exactly.
So what we're seeing here isn't that we stop when we generate a red token as much as we generate like maybe 20 tokens and we're validating all of those.
Yes, yeah.
Okay.
But it's not usually as much as 20.
Yeah.
It'll be fewer than that typically, but yes. Cool. All right, it sounds like everybody's on board. All those are great questions. Let's actually see the algorithm, which is not too much more complex. It's almost exactly what we're talking about over here. This is the thing on the right, but we can kind of talk through it. We have 2 models, which are MQ and MP. Okay, yet more notation. M here stands for model, which is not normal notation. Pi is usually the one that we use, but that's fine. MP is the original model. It's big and it's slow. MQ is our new draft model. It's small, and therefore it's efficient compared to the original model. Now, how much more efficient? That's the big question. That will sort of control how fast we can get, right? If it's not much more fast, then speedups are really bounded. If it's way, 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 way more fast, then you'll probably get rejected a lot because it's probably a much worse model. It'll have very different distributions. So this is kind of what's going on here. Okay, so the very first thing we'll do is generate gamma tokens from our cheap model MQ. So gamma is this fixed number that you guys were asking about, right? This could be 5 or 10 or whatever number of tokens that we just generate. We're generating these autoregressively from the small model, so this whole process is fast. Everybody agree? Okay, now hopefully it's faster than generating one token, right, of the original model. If it's not, then we haven't really gained anything from the process of doing this. Okay, so we're generating these gamma tokens. We'll check what was accepted, and by check I mean you can see the line over here. You're essentially saying, hey, let me see what is the largest number before this subsequence is very different compared to the original sequence. And that's what you're seeing over here, which is this n is the minimum of all the indices from 1 to gamma, right? The first place where we've gone too far and we need to reject. That is n. So we have two numbers happening here. Gamma is this fixed number of generated tokens from the draft model. N is the point where we have to go reject, or the point right before we go reject. So this n is really dependent on the actual generations. Gamma is fixed throughout this process. Okay, so we figure out where this n is. And as you can see, I'm creating this threshold, which is p over q over there. And this is exactly what you need for rejection sampling, right? You want to match the original distribution. And this is what you're getting on average. Okay, so a particular token may not have exactly the same distribution as the one from the original model, but on average will be the same. Same basic idea as doing Metropolis Hastings, which is a very standard kind of sampling technique. Okay, so we do this. Then we'll generate one extra token. And then finally, right, we'll have our total thing that we created all in one run, x1 through xn, plus our extra token from the original model. Everything that you're seeing in the algorithm is just created to make sure that we're enforcing these rules of you should reject if things get too different, and you should create as many tokens as you can up till that point. Okay, so that's pretty much all that it is. There's nothing super special. It's just this picture that you saw before. Everyone should kind of walk through this algorithm to make sure they're feeling comfortable with it. You can actually prove everything that you'd like here, which is to say you can prove that the tokens you get on average come from the same distribution as the original model. It's also kind of fun to try to analyze, again, on average, how many tokens you created. What is the average value of n? So the results are pretty good, as you can see. And in fact, pretty much everyone does this. This is all using T5 models, which are an older class of models. But notice the values of gamma, right? So we can set this to whatever value we want. But again, if you make it too big, you're wasting compute of the small model, because you'll always get rejected far in advance of that number. On the other hand, if you're making it too small, you might be leaving something on the table, because you might have been able to generate more tokens and get them accepted. Everybody see what I mean by this trade-off? So you have to figure out a good value of gamma. These are 7s and 5s over here. And then alpha is that kind of extra ratio that you're getting. So this is the average number of things that we get in total. And speed ends up being 3, 2, depends on kind of which particular model you use. Notice that here T5 small, base, and large are different things that we can use for the draft model. So we're using smaller to larger draft models, different temperatures, so that's just another hyperparameter. But basically the question becomes like, hey, should I use a more powerful draft model, which is going to keep me from being rejected as early, but it's slower itself? Or should I use a smaller, cheaper model, which gets us rejected more often, but is much faster? That's pretty much the only thing that's being addressed here. Lots of different possible extensions. And again, the only other thing that we've been talking about is what kind of smaller models should we use. Go for it.
I had a question about the algorithm part, because it's like, so your criterion for accepting or denying a token is based on uniform distribution, right, from 0 to 1. So wouldn't it be possible in an edge case scenario where you're just drawing like 0.9, 0.9, and then you just never accept the token because it never reaches that 0.9 threshold?
You can have that happen in one trajectory, but on average, it won't happen. Do you see what I mean? Yeah. So with low probability, anything can happen, right? You get rejected constantly, right? But on average, it won't happen. You have to get very unlucky for that to take place.
If that's the case, why not just set a threshold of 0.5? Because the expectation uniform from 0 to 1 is just 0.5.
No, that won't work. Okay, let me think about writing down why that's not the case, but that should not be possible.
Okay.
Yeah?
What is alpha in it? Alpha.
Oh, alpha is like the average number of extra tokens that we're creating per. So this is like saying, if I run my algorithm and I'm counting the number of green tokens, right? On average, how many of those do I get?
See, on average, like for example, if the number of green tokens per line is 3, then you take an average of that distribution and you compare it with the original distribution.
That's pretty much what's going on, yeah.
Is there a threshold which we consider here?
Well, this is implicitly the threshold, right?
Ri?
Yep.
Okay. If this is greater than this,
This is not the threshold itself, right? This guy is the threshold. Ri is actually just one of the samples that you're getting over there.
okay. So like this is the threshold.
But the reason why that's the threshold is that's the ratio between the two distributions we're considering. P, the original language model, the one that I actually want, and Q, this draft model, which does not have the same ones.
Okay. So like for example, it should be a low bound, right? It should actually be a low bound.
That is essentially what's happening, yes.
Something should be greater than this in order to be accepted. And if it's
Yeah, and that's where this sampling the uniforms is going to come from.
okay.
Yep.
I just want to know if the speed column represented the absolute speed up of the model's total inference, or just the inferences made by the small MQ models.
I think it's everything, right? That's a good question. I haven't checked what this column means, but we should. But yes, that's intuitively the only thing that should matter here. It doesn't really make sense if it's just computing a speed up on something as a part of it, right?
Yeah.
But yeah. Cool. OK, so that's all I wanted to say for speculative decoding. Try implementing the algorithm yourself to see if it kind of tracks. Let's briefly talk about 2 extra topics, which are getting back to the questions you guys had earlier. So I mentioned this one. We can do a little bit of sort of adaptation to the input. And the only thing that we'll really do here, although there's many ways to do this, is to basically say, hey, do I really need to run all of the layers of my model? Right? So that's the question in general. Why do I need lots of layers? And the answer is, well, because you need this very high model capacity to try to actually solve whatever challenging prompt the user's given you. But you don't always need that. In some cases, whatever's being requested is something that's actually very simple. So when it's safe to do so, maybe I can sort of jump early. Rather than running through all my layers, maybe I can do something different that's hopefully a little bit cheaper. So we're going to do that, basically. And here's the picture. Instead of running every single input and each new token that I generate for all the layers of my model and decoding at the top, maybe I can decode early, right? There's nothing stopping me from doing this. I can attach the decoding component to any of the layers that I have, right? And all of the layers are really just processing the current token that I'm working on. So maybe, in some cases, if there's something really simple, I can just jump out after a few layers. Everybody agree that this is possible? OK, so now you might say, hey, why don't I always jump out early? Which is the same thing as saying, hey, I'm going to use a language model with fewer layers, right? That is equivalent to saying I'll always get out early. Well, I mean, the basic answer is you won't have as good performance, again. So really what we want to do here is to have the flexibility of running through all the layers in cases where I need to, and running through fewer layers in cases where it feels like the next token is something very obvious. And that's essentially what's happening here. Now, I have to figure out some way of predicting, right, whether the current token I'm generating is going to require all the layers or not. And we can essentially create certain constraints that tell me, hey, you're at high risk of doing something bad if you jump out early, et cetera. So this is a fairly simple technique that you can also use to cut down how much compute you do at inference time, and therefore let you finish up much sooner. And again, same principle. All we're really saying is instead of having to wait for each layer to finish before I move to the next layer, we just kind of cut ourselves off and say we're done at some point. Cool. So this is another technique that you can do for this. Now, let me introduce one more thing, which is similar to what you guys were saying earlier. Same deal, right? Another problem that we have is we'd like to generate multiple tokens at once, but we can't because we have to wait for the current token to get created before I can predict the next one. OK, so there is a technique that can sort of get around this. It's called Medusa decoding. Here's the basic idea. What we're going to do is instead of just saying, hey, I have a prediction head that is generating the current token from all the layers, I'm now going to introduce some extra heads. And these extra heads are trying to predict simultaneously what will be future tokens. So I have my regular language model head. It's predicting the current token I'm working on. But I'm going to create some additional predictors, 2, 3, 4, 5, that will predict tokens 2, 3, 4, 5 past the current token. All right, everybody okay with that? It's as if we are generating multiple tokens at once, but each of these different heads is trying to say, yeah, these are the future tokens. Okay. In fact, we're not going to typically generate just one of these tokens. We usually have some kind of decoding principle, like let's say top k. Top k is just saying, here's the list of the k most likely tokens that I will predict right now. And that's what you're seeing over there on the top k predictions. I have the current token. The top 3 is it, I, as. And then I have another top 3 for the second, third, fourth token, because I have 3 extra heads here. All right, everybody okay with this principle? Now, doing this is not by itself hard. The thing that's challenging is I have to assemble these different tokens that I have into some coherent actual sequence. So this is the bit that gets more interesting. I have some candidates that come from taking elements, right, of each of these different token positions. And I have to figure out which one's the best one. And then again, what can we do here? Well, assemble a bunch of these guys. And again, do something like rejection sampling, or something different that we can look at. Maybe I can run another form of attention here as well. See what looks potentially good. So that's the only idea here. So this is something that's quite powerful, but it's not used all over the place currently. Like I said, just go ahead and run multiple things in parallel, and then assemble into a full sequence. And however many heads you've been able to put together and still generate a good set of candidates, that's your speed up. So if I can add 3 extra heads that predict the next 3 tokens past the current token, then I have 4x speed up, right? Again, assuming that I haven't broken everything and I'm constantly getting rejected. So similar principle. Notice that pretty much all of these were doing almost all the same thing. They were all trying to get around this token by token kind of prediction problem, because that was the slow part. So the methods that we've talked about so far are just doing exactly this. Either use some cheaper model to generate a bunch of tokens at once and check if it's OK, or go through fewer layers when I'm generating the next token, or predict multiple tokens at once and hope that it's OK there too. Cool. That's all I have for today. So I'm going to stop here. I'll hang out, and if folks have questions, I can answer questions. If not, you guys are free to go. I think this is going to be our shortest lecture.
As you're predicting this token,
Yep.
feed this one into the second head.
Well, like, if I do that, I've lost parallelism. I have to wait, right? Do you see the problem?
So like you're saying that all 4 of these get generated at
Yes.
the exact same time.
Yes.
And the way they are doing it is by using the rich embeddings.
Yep, exactly. Yes. So I have to generate all of those at once. If I don't, if I wait for them to come in one at a time, I'm back to where I started.
Is it similar to like PyTorch code? I'm trying to think. In this one, you just simply remove the classification head or the head and just make
Yep.
different head.
But you're not really removing it. You're just adding some pieces to here, right? This is already happening in the original language model. So this is all frozen, right? Nothing has changed here.
Which part? This part?
This entire left part is frozen. This is your original language model with no changes whatsoever. And what I'm doing is I'm attaching a bit that comes from here, right? So I'm saying when I get my second to last layer or last layer, those are just the embeddings you were describing. I'm also going to pump those out into this new module. I don't change anything happening here. I just take this output from this layer and go ahead and do this process all in parallel. So I'm going up in parallel and to the right in parallel. So the only thing that we're doing there is we're saying, hey, look, I don't really need the full power of my big language model all the time. Sometimes I can predict things very cheaply, right?
Adapt per token based on the confidence level the model has with respect to that.
Well, not just based on confidence, based on some other rules that I'll create. And those rules are some custom things, some heuristics.
So like this can be very different compared. The main bottleneck here is that the rules and the constraints should be good.
Yes,
I think that is the main.
exactly.
If it's bad,
If it's bad, then yes, you'll have a very low quality language model. Yeah. Now, okay, I mean, these are all heuristics, right? So they don't always work. They work sometimes, they don't work other times.
makes sense. The short way to get it is through the first one, speculative decoding. Like the short.
That one is consistently going to be and it's not adapted. But implicitly it kind of is.
So it's more expensive.
It's more expensive. I'm running an extra language. And then doing some extra operations. But those are not so bad, right? Because like, it's dominated by the speed. There's no extra model for it.
So like that's what I mean.
Well, I'm creating more heads, right? And all those heads are now going to do some extra work, but not to the extent of a full nothing. And then I have some rules to check the generations. The only question is, how often you're not going to keeping track. Because it's very easy to create a bunch of candidates that are all bad, right? And then you're stuck.
Yeah, it's when. This is just the joke.
Pretty quick. It's not unusual. So like pretty much all of the buildings LLM models will do speculative. And we don't really know what's the case for I don't know what OpenAI
I went toe to toe with my friend again, and he beat me on turn 94.
Also has a question about like the logistics of this class. Because I just checked.
Yeah, we could talk
like
about
anything on Wednesday.
No.
Like anything like scheduled after that. Okay.
Yeah, just a little bit. Just do the last day.
Okay.
There's no exam.
Okay.
Yeah, I was gonna ask about the by that weekend.
Yes. Try running the expectation calculations to see that you're getting a sample and see what happens if you do it all. Try the math, you'll see what happens. But if you don't see it, then let's chat. Yes. Yeah, that's that game. Let's say gamma uses 5 tokens from my graph. Auto-regressively, one by one, that's faster because that one's cheaper.
Then you'll really have to, yes, you can, because each one, all it's doing is shifting things more and more towards what the correct representation is to get a more refined Zero cents.
Well, the original model itself is just a problem, right? And I can plug stuff into it and see what it says. I can say things like, oh, if this is the token that was generated, this has some probability of showing up. There's nothing stopping me from doing that. That's actually a training. So I can do this. I can take the generation that I'm coming from the graph. You just plug them into the original. Now, why is that good compared to generating them from the original? Well, if I generate 5 of these guys, I'm done. And I have 5 of those guys. I can run. Oh, yes. We're literally giving it this stuff that's going to be. Just like how, the previous token goes into the next generation of the original model. Now it's going to be the previous 3 tokens. But more about it. Yeah, just as they're plugging in, right? So you're used to plugging in a bunch of things. Yeah, come on. Same principle.
Not even making eye contact with
But there is no stuff over here. The original model is of its own. If we don't do that, then it's as if we're just using the small image. But it's often not good enough, right? We want something more powerful.
Alright, so today we were starting a conversation.
Always complete. I can agree with that. In fact, I have turned it right this year. Yes.
I should probably read the actual.
Through the web interface. I haven't tried the API.
I was going to read that.
For this one, we can't pass in
Read what?
Insane.
So what is the equals like isolation exit from particles that are
You could do that. Or that's what he's at.
for
So
allergy.
interesting that you just say, oh, that's the problem. It will try to act like this, even though it's not really something.
Trying to do.
Yeah, so I don't know, I tried like the, like, you know, how
I
to
assume
get
there's
like
very
fire.
shady.
So it's no temperature,
Medications on the spices and
and if you say like,
the Chevron doctrine,
you have this strong, so you pump it out.
the labeling.
So the thing that is like this as well, if the free version is like
It's more fun if you make it wrong, but you can make it correct. You're doing it correct, so you're doing it correct. But yeah, I mean, yes, okay, so like, you don't always have control of the needle temperature, but like I said, you can simulate it by like forcing it into the prompt itself.
yeah, it did say that it can't change the temperature in the backend, but it will try and.
You cannot rely on like, saying, oh, the temperature should be 0.3, and expect the actual model to really do that. But anyway, it will try to behave as if you have that, right?
And the other thing is,
Essentially have,
I don't have CPU.
For the character level, you should be able to run this without using.
Yeah,
It should be fairly fast with at least on like real.
it was really fast, so that's why I'm worried, like, that's okay.
Yeah, because like the big problem that we have is if you have, 50,000 tokens in vocabulary, things are big. But if you have 50 characters, it's now
if there's some way, like, if there's mass vector,
We can predict the existence.
that's the whole point of NanoGPT. You can do it on CPU. So you're good.
there will be a token. They will convert your model.
I think also things I believe the external content is safe.
No, not. So when I was testing,
Oh, there's gonna be data, like, we can tell.
I actually.
For example, say that you're doing, 7 focus. You create the first 3. All the map directions. You would do that. You don't have to wait for you to create more afterwards because you already know this is the answer, right?
Should I report like the numbers? I would imagine quite a bit. You don't want
Oh, you can do it too, but no, just all it's asking you for is saying, hey, like, you're generating these one by one. If the first answer is correct, then if the first answer is wrong, then the next one correct for you.
So for instance, free watchdog is real. But I mean, how should I change it?
The point here is that you don't want the model to give you the same answer. So you're changing the temperature in a way that hopefully will give you the confidence. But you can also generate the confidence in the temperature.
Ask for advice.
What if ChatGPT give me? Yeah, I think that actually when it asks, we can develop a when it asks questions.
I mean, maybe change your efficacy to something that's not just basic raw protein until it's unknown, right?
Oh,
For example, you could do that. You could do it crazy.
so I can do like
Yeah, exactly. There are also, even in raw protein cases, where it'll mess up. But you would have to play with it. The models have gotten much stronger, so it's not like tricky. But still, you can do it with raw protein and frogs, like raw protein.
like also when I was trying this problem, like so I used the model I used is GPT-5.
Yep.
But the recognize the
Yeah, GPT-5 is pretty powerful, so it's not. It's still foolish, but it's more.
I don't do that but yeah, but I want to try.
What you need to do for raw protein is create something that's very useful for a language model right off the bat. Very long, or the relevant information, and then you run Right, so that's how you do it. Even though it goes from
It means that I don't have to give you very
I think, yeah, you can avoid using route 13 itself and move to something different. Then you can for sure fool it. Like that, no. But even for route 13, it's challenging enough. That's what I mean. Like, but you have to create a hard enough prompt. It can't be like my simple example. Yeah. Actually, like whatever.
I also think that
No, it's you. Yeah, the only thing that we might do is having the camera is print out a poster how the day will be presenting in the lobby. But it's not confirmed yet because I have to reserve space. I'll release this. There's no sign up sheet really required because it's not taking that'll be just more you guys. The except for presentations will actually come. The final project is due on the date forever, but
Okay,
there's no
y'all have never heard of the movie Soylent Green? Okay.
the only situation where we
So
present
the
the final
whole
project
point behind
is
Soylent is that there are different Soylents that are available.
it's not yet.
They're effectively just meal replacements in a future apocalyptic world where only
It's going to be a report.
what's happening right now.
Sure. And then there will be a phase earlier on where you guys send me.
Soylents are starting to get more expensive as food is becoming more accessible.
Yeah. Well, more, but like, here is what we plan to do. You probably won't have the equivalent of an abstract yet.
However, some people are starting to protest it.
No, it's a presentation.
Some new Soylent goes on
One is the opportunity for you to look at, one is the project.
Unfortunately, protesters are also going missing. So around the midpoint of
Well, your presentation is all for pre-existing. And your project is for why you using your own.
it sounds so heavy.
No, the project is nothing new. Because we haven't released that information. That will happen this week, but the actual proposal date for the project is like.
I was like, I've seen it firsthand.
You guys haven't seen it?
I've seen it firsthand.
Yeah, I mean, it's a bit online, which is the timeline for the project. I don't even know if it's sure. It's not good. I don't know what the official last name is. But 9th is our last.
They're not named meal replacement substance.
And I will kind of make it well, just to give
And
us
I'm just like, why, this is horrible, I can never have this.
You will be doing a presentation. So, throwing up.
I watched it. My parents said they watched it together when I was young.
And then you will submit your projects right on, which is the last day. That's pretty much all we have.
I feel like we need to figure out the journal post. Well, no, actually,
Yeah, so it's actually definitely the whole way.
we just set a time.
For the presentation, you're just telling me what you're gonna do.
That's
and you're
the main
gonna
thing we have
actually do the presentation.
The other
For the project, you'll have
actual
proposal,
project.
cert, and then the actual project, right?
He say that he
And those are all the things.
released the information for it, or?
Well, you know, they should have.
We wanted something multimodal.
A lot of us here are interested in this. Epic released the comic.
It can be, it's not. Like, if you wanna do like, algorithmic things for elements, you're welcome to. But applications are very different. If you wanna do that.
So we can't,
Easy.
we can't do it all.
Do we need to run it?
Probably.
I don't think they can release the foundation.
If it was.
Talk to me about that, I'll try to do my best to help. We'll see what's possible. I just can't promise anything because if everyone says, hey, I need 8 hours,
James Dot.
Yeah.
It says project information.
Oh,
So yeah, if you guys are doing something,
But-
you
but
can
we have to make
time,
sure
and there's a good reason for it. Something to do.
I was just saying.
So do we want to do themselves there, because that's what it would be.
Yes, I think.
We'll find something that's not your own. Like I said, just propose something.
Yeah.
I think that's kind of hit my PhD.
I mean, that's kind of my PhD.
Oh, fun.
Although I'm also looking into
actually predicting
But
forwards.
still, I mean, I'm
So
doing.
each of these heads is giving you choices for the word in some position. Right, so over here, your current position you're in, right? You're getting three choices for it. Each of these could be the first
I wasn't trying to say
words.
Basically, probability probabilities.
Oh, good.
Yes,
You're in the right
there's other
place.
decoding rules. Op K is not Q.
Okay.
But this is pretty common. Okay, and you really predicted, so this first head is predicting the second token to come after the first head. The second head is predicting the third token. The third head is predicting the fourth token.
I thought,
So as you can see, what we're really predicting here is four tokens.
isn't it part of?
So the L1 is predicting after it works,
I haven't looked at
these are the three options.
the project
distributed.
proposal, the project information is
Well, actually, it's based on a guess of what the future will look like. So this head does not have access
Say anything about
the first.
presentation having.
I mean, yes, the presentation is, like, the presentation.
And it can't have access, otherwise we're back to our objective. I don't want to wait for this thing to be completed before I go over
It
here.
just says, like, familiarize yourself in class with me.
Was there anything guesses? Right? We're gonna train this, they're not random. Guess typically what is gonna be two tokens in the future. It's not in general.
It's not, there's nothing.
All I'm saying is it's hitting it from forward to back.
Yeah, I see.
So you create some special distributions that say, hey, what do I think will come for two tokens in the future, three tokens in the future, four tokens in the future? That's what you're trying to do.
It is, I'm serious, we can connect it back. All these variables that's-
So that's why when we go to notice that these candidates over here are forwards.
Sure.
Those forwards come from picking one of these right here.
Well, if you want to do
So
that.
this is now something that should be a candidate for token sequence for us now. And what we're gonna do here, we're gonna say, okay, well, how likely are these guys to show up? Just like we did for speculative decoding, we said, okay, you know, our small model generates four tokens.
We use show
I did not count that we have
Depending on what else, of course, yeah.
and it was also a language.
Given a higher scale of data, essentially, a lot of that.
It's a little language model, right? It's a little language model still.
Then we were running auto-regressively on SLM, but
Sure.
it is not.
Sure, so now we're creating errors in distributions. Previously, the error was small language model has different distributions for sampling compared to big language model. Here, the error is gonna come from way of predicting things in the future, right? That's
So, I
different.
mean, the question is.
Either way, it doesn't really matter. We're doing this process, and when stuff doesn't make sense, we can just throw it, right? Not in real time. We can train these things in such a way that we're better at predicting these things, but not as we actually do it. These types predictably predict. We create the candidates, and then we say, hey, is there any candidate that's good?
So during training, we train LM and we also simultaneous, sequential.
Yeah, so we can do that during training, there's nothing stopping us from saying, hey, create this head that's good at predicting what's gonna be two tokens in the future, right? So that's nothing stopping us from doing the process. But during inference time, it's not fixed. Just like how, you know, for predicting bad tokens and speculative decoding, I cannot on the fly train the draft model to do it, right?
And rejection, the rejection sampling, like this and this. So all this rejection you are or is there any, if
Well,
it's.
the LLM is a distribution. That's all that the LLM itself is. And all we're saying here is I have sampled a bunch of stuff from this different distribution. Is this still compatible with the original distribution? If I do a bunch of this stuff on average, is this still the original LLM, right?
So we are telling, we are original LLM if the SLM is matching.
Yep. But again, that's tough, because I have the tokens already. So there's nothing stopping me from This is,
You're right, it's just kind of
this
like.
is rejection sampling. It doesn't come from LLMs, it comes from the world of sampling from different distributions compared to whatever distributions.
No, like the rejection, is it, we are giving the prompt to LLM that is it correct or not?
To identify a problem.
Oh, no, we're doing some more. We're using the actual probability.
Yes.
Of rejection sampling.
Yeah.
And it is actually encoded in the algorithm that I showed you.
Yes.
So it is literally here.
I mean, I have the skills
This is
of
rejection
optimization.
sampling
I
here.
did performance optimization.
Check out what's going on here, but really what was happening is we're saying, hey, I generated stuff from this distribution. but I really want to see
The best thing that I
so I should really weigh things.
The best thing I
sometimes
can
really
do is if
overview.
someone hadn't already discovered it, I would have known the SRAM.
But I can just sort of throw them out some percentage of time.
Well, aside from
Until
the
probabilities.
softmax,
That
I would have had to figure that out.
So I think basically how he poses us
It is just an algorithm that we're doing. But no, we're not running stuff through another normal thing. Although people do that kind of thing as well, but I think fundamentally it's different.
We can do that as well.
You can, but it wouldn't give you this. The point here is that this is something where, on average, you really are getting stuff that is just as if it came from the original model. And this is something more provable. If you run it through an LLM and say it's good or bad, couldn't work,
Yeah,
but
and
there's
I
no
think there are some things to consider in this space.
So yeah, all we're doing here is
One of the
saying, hey, do
questions we have
something
to
incredible.
ask is sort of what
And
has
see
been
more.
done.
Right, that's it.
Because this is a lot of what has been done, and it does help to elucidate sort of the structural constraints that we'll be using.